Hello students, welcome back to SapphireBlueChemspark. Today let us start our session from the chapter Coordination Compounds in Organic Chemistry. So the previous sessions we have discussed a lot of things about coordination compounds. Today we are going to discuss about the nature of bonding present between the central metal ion and the ligands. According to Werner theory, we discussed that the dative bond is present between the metal ion and the ligands. But Werner's theory fails to explain about why certain elements alone are capable of forming large number of coordination compounds. Also, he fails to explain about the magnetic and optical properties of the complexes, and also fails to explain about the directional property of ligands. So, to find out the answers of these questions, so many theories put forwarded to explain about the nature of bonding in coordination compounds. So, we have valence bond theory, crystal field theory, ligand field theory, molecular orbital theory. All these theory that explains about the failures of the previous theory by the followed theory. So today we are going to discuss about valence bond theory, and we have one more theory that is called crystal field theory. These two theories, they differ in their way of presentation of formation of the bond between the ligand and the central metal ion. Crystal field theory and valence bond theory, both of them, they discuss about the nature of bonding in metal complexes in two different manner. VB theory, it discusses about the hybridization followed by the overlapping of atomic orbitals of ligand with vacant hybrid orbitals of metal ion. But crystal field theory, it speaks about the formation of a bond between the metal ion and the ligand is purely ionic. So, VB theory says about covalent nature of the bonding between the metal ion and the ligand, while the CFT, it speaks about the formation of ionic bond between the metal ion and the ligand. So, in these sessions we are going to discuss about VB theory and CFT only. The ligand field theory and molecular orbital theory, that beyond the scope of your level, and hence those theories are just omitted. Valence bond theory. Valence bond theory put forwarded by Linus Pauling. According to him, there is the overlapping of atomic orbitals of ligands with hybrid orbitals of metal ion. So, we know well the central metal ion, they have their specific coordination number that may go from 2 to 6 or even sometimes 7. So, when we speak about the valence bond theory, the hybridization is an important aspect of this theory. Okay, what do you mean by hybridization? Hybridization is the phenomena in which the atomic orbitals which are differing in energy mix up together to form hybrid orbitals of equivalent energy, or we can say same energy. Metal ion, first of all, it forms the respective number of vacant hybrid orbital. That respective number of vacant hybrid orbital depends upon the coordination number of the central metal ion. So, here the bond is actually formed by the sharing of electron from the ligand to the metal ion. So, when electrons are shared between ligand and metal, we can say it is purely covalent in nature. But the thing, covalent bond actually undergoes the mutual sharing of electron. But in this case, metal ion able to provide the vacant orbital to which the ligands can share its pair of electron to make a covalent bond with the metal ion. And hence, we may find the ligands has to provide each ligand, whether it is a negative ligand or a positive ligand or even a neutral ligand. They should have a capable of donating at least one pair of electrons. And those pairs of electrons should be received by the metal ion. So, metal has to provide the equivalent number of vacant orbital. So, before forming the vacant orbital, metal ion, that is, there is a mixing up of ns and n-1 d orbital or nd orbital. So, in such cases, the metal ion usually they have the orbital electronic configuration of n-1 d and ns orbital. And followed that it can have np orbital as well as nd orbital. We know the n-1 d orbital is an penultimate orbital. It is a penultimate orbital. Ns, np and nd are ultimate orbital. So, the n is the respective period number. Suppose if at all I am taking this is the fourth period, I can have where n equal to 4. So, when you substitute here, we may find 3d orbital, 4s orbital, 4p orbital and 4d orbital. So, these are the available orbital that can undergo hybridization to form the respective number of hybrid orbital depends upon its coordination number. Okay. So, this is 3d orbital. It is the inner orbital of the complex because this is the fourth shell but this is the third shell. Third shell is always inner to 4 and hence we can say n-1 d orbitals are inner d orbital. And this is ns, np, nd. This is what the outer shell, that means the valence shell of the metal, and hence these are said to be outer shell. So, we can have the hybrid orbital by mixing up of n-1 d, ns, np, or we can have ns, np, nd orbital. So, there are two types of mixing up of atomic orbitals of metal ion as a result of formation of hybrid orbitals because of n-1 d, ns, np. Such orbitals are said to be inner orbital, and the complexes formed as a result of these hybrid orbitals are said to be inner orbital complexes. And in these inner orbital complexes, we know the d orbital that can have the electrons start from 1 to 10. The inner d orbital, as it has 1 to 10 electron, we can say from the series 3d1 we take scandium to zinc. What happened? Number of electron progressively increases. So, we may find d1 to 5, they can have the 5 unpaired electron. After 5, then the d orbital gets paired with 6 to 10. So, scandium to manganese, they might be a formation of unpaired electron. But after that, the iron to zinc, the d orbital is getting paired up with each orientation. So, number of unpaired electron decreases. So, depends upon the availability of unpaired electron present in this n-1 d orbital. It gives rise to the two types of complexes, namely low spin complexes or a high spin complexes. What do you mean by low spin? Where the number of unpaired electron is in least number. What about high spin complexes where the number of unpaired electron is maximum? So, when the orbital has paired electron, the spinning of electrons will be cancelled one another. But when number of unpaired electron increases, each electrons of the orbital has its own spin, and hence the spin of the complexes also increases. So, we got one of the complexes of the type inner orbital complexes. What about outer orbital complexes? Outer orbital complexes where when the ligand is unable to pair the electrons of inner d orbital, then it can make use of the outer d orbital for the hybridization. So where you will find the mixing up of NS, NP and ND orbital. So when these atomic orbital mixes together, then it gives rise to the formation of outer orbital complexes. So from the VB theory, we can have the two different types of complexes, inner orbital complex, outer orbital complex. When you have outer orbital complexes, definitely there would be too many number of, there is a possibility of presence of unpaired electron in its n-1 d orbital. So those complexes are said to be high spin. But when n-1 d orbital is involved in hybridization, we may expect there might be the possibility of unpaired electron is less, because sometimes the ligands, they may push the n-1 d orbital to pair up. That's why the number of unpaired electron may decrease. So the formation of inner orbital and outer orbital complexes, which may result in low spin complexes as well as high spin complexes. Okay, we got the hybridized orbitals of metal ion, and we have the ligand, and the ligand, they have filled orbitals. All those ligands can have the electron in its filled p orbital or even s orbital electron, because most of the ligands which were coming from only the p block elements. In p block element, the valential is composed of ns2 np1 to 6. So always s orbital is filled up. The p orbital alone can have their own electron. So those electrons can only be shared for overlapping with central metal ion of hybrid orbitals. So such overlapping is always linear overlapping, or we can say axial overlapping. The axial overlapping or linear overlapping of the ligand with the central metal ion, it leads to the formation of sigma bond between the metal ion and the ligand. These hybrid orbitals are usually directional in nature, and hence this hybrid orbital that can orient in a given space in definite directions. Because of this orientation, that may give rise to geometry of the complex. And the next one, the ligands like cyanide, carbon monoxide, ethane 1,2 diamine or ammonia are found to be somewhat stronger. So such ligands, they can easily pair the n-1 d orbital, that is the inner d orbital, to avail the vacant d orbital. But some cases, the ligands like halide ion, Cl-, F-, Br-, sometimes even water, they unable to pair the d orbital electron, that is the inner d orbital electron. Such types of ligands are classified as weak ligands, and cyanide, carbon monoxide, ethane 1,2 diamine, ammonia, these are just classified as strong ligands. So depends upon the strength of the ligands only we can have inner orbital complexes or the outer orbital complexes. Strong ligands always pair up the d orbital electrons, while weak ligands never pair up the d orbital. It can avail the vacant nd orbital for their hybridization as well as overlapping. These are the important points we discuss about valence bond theory. So let us find some of the examples of the formation of complexes according to VB theory. Let us find some of the complexes to which the VB theory is applied. So let us take first of all the complexes having coordination number 4. So I have taken the complexes of nickel only. In these cases, you may find how the geometry, hybridization and the magnetic property of the complexes varying from one to another. So let us find first of all nickel tetracarbonyl. I said carbonyl complexes always having zero oxidized metal ion. This is why, because the carbon monoxide is such a strong ligand, so that it can push up all the s orbital and the d orbital electron together to avail the vacant orbital. So due to the presence of carbon monoxide, nickel, it is in zero oxidation state. Okay, what about the atomic number of nickel? Nickel atomic number is 28. So for the 28, 18 electrons are present in its inner core of argon, and the rest of the electrons are distributed in 4s orbital as well as in 3d orbital. So it has 3d8 4s2. After 4s we have the 4p orbital, but it is empty. We have to always make use of the outer orbital also. That means the fourth shell orbital to be availed. This is why, because we need more number of vacant orbital. So when we have the shortage of d orbital, we have to make use of 4p orbital. That's why when you write the electronic configuration of any metal, the transition element, you should always write 4s orbital, 4p orbital, even we can add 4d orbital. But in these cases, I am going to take only the coordination number 4, and hence I didn't consider 4d orbital. Okay, now nickel, it is in zero oxidation state. So none of the electron will be lost by the 4s orbital. And I said carbon monoxide is the strong ligand. So what it will do? It will push up all the electrons of d orbital as well as 4s orbital together. So what happened? This d orbital electron get paired up, and to the vacant orbital 4s orbital electrons is being filled up. Therefore the 3d8 it becomes 3d10, and 4s it becomes 4s0, 4p0. And what is the coordination number of nickel? 4. So nickel has to provide 4 vacant orbital. So one s orbital we got because of the shifting of 4s orbital to the 3d orbital. So we have one 4s orbital and 3 4p orbital. So mixing up of 4s and 4p atomic orbital, it gives rise to sp3 hybridized orbitals. So you may find there are 4 sp3 hybridized orbital of nickel in its zero oxidation state. So to this vacant orbital only, the carbon monoxide is going to provide its unshared pair of electron, and hence that makes the filled hybrid orbital. So the overlapping of sp3 hybrid orbital of nickel with the filled p orbital of carbon monoxide takes place, and hence we have the complex nickel tetracarbonyl. So in which we have to write down the summarization. What about its geometry? What about its hybridization, magnetic property, as well as spin of the complexes we have to summarize. So the hybridization is sp3. Geometry for sp3 it is tetrahedral, and spin of the complex you may find the d orbital has no unpaired electron. We have to find only the d orbital. We are not supposed to find the overlapped orbitals. Okay, so spin of the complex is low spin as it has no unpaired electron, and moreover magnetic property, once again it is diamagnetic. This is why the d orbital has no unpaired electron, and hence the magnetic moment of the complex becomes equal to 0. Let us take the next complex, tetracyanidonickelate 2 ion. So nickelate 2 I said. So 2 means that oxidation state of nickel. So nickel in this complex it is in its +2 oxidation state, but in the carbonyl complex it is in 0 oxidation state. Once again, whatever the steps we have to represent for this complex also. So its electronic configuration 3d8 4s2 4p. And it is in its +2 state. So the 4s orbital electron is being lost by the nickel. So we can write nickel 2 plus, where it has 3d8 4s0 4p0 in its +2 oxidized state. And Compare the strength of the ligand cyanide. It is somewhat, I said, strong. So what it will do? It can pair the d orbital electron, because d orbital it has two single electron and those two can pair up. So it forms the D8 of nickel in presence of the ligand, where one of the d orbital, s orbital and the two of the p orbital is mixed up, because the coordination number is 4. Nickel has to provide 4 vacant orbital. As the electron pushes to the d orbital, we have the vacant orbital of this one s orbital, and need to take 2 more p orbital. So that forms dsp2 hybridization. You may find the comparison. D orbital usually 5. I have only 4. So one of the d orbital is present in its hybridized form. So d, 1s and 2 p orbital are composed of, that is hybridized to give dsp2 hybridization. So it for the nickel tetracyanide complex, we may write all the 4 cyanide ligand, they give their pair of electron to the vacant hybridized orbital. So we are getting the complex. And just to distinguish the electrons of metal and the ligand, for metal it is given that upward arrow and downward arrow. For the ligand electron it is simply given as a cross sign. Nothing make difference but. Okay, what about the hybridization? DSP2. For the DSP2, the geometry is square planar. These and all you have to remember. And once again, the d orbital has no unpaired electron. So the complex is a diamagnetic as well as low spin. So its magnetic moment is also 0. The next complex, nickel NaCl4 2 minus. Once again, the chloride is negative ion, and in this case also nickel is present in its +2 oxidation state. Same information ditto, but comparing the strength of cyanide with chloride, what we said, chloride, bromide, iodide, even water and all low, that means weak ligand. So they are unable to pair the d orbital electron. Here cyanide pair the d orbital electron, that's why we got the 4 d orbital with the 8 electron. But in this case, as the chloride ion is the weak ligand, it is unable to pair the 2 unpaired electrons of 3d orbital. So what it will do? It has to go with available vacant orbital. What are the vacant orbital available? After the loss of s orbital electron, nickel becomes nickel 2 plus. So the available vacant orbital are 1 s orbital and 3 p orbital. As the coordination number is 4, it can mix up. So the 4s and 4p orbital mix up to form sp3 hybridized orbital. So in the case of tetrachloridonickelate ion, the hybridization is sp3. So to the vacant hybrid orbitals of metal ion, the 4 chloride ion provide its unshared the pair of electron to their vacant orbital, and hence we are getting the complex. So in this case, hybridization is sp3. Geometry, sp3 means tetrahedral, so it is tetrahedral. And the magnetic property, it is paramagnetic. Why? It has 2 unpaired electron in its d orbital. So those 2 electron we have to take it in its magnetic moment. Magnetic moment formula, mu s equal to root of n into n plus 2. This is what we discussed in our D and F block elements itself. So mu, where n equal to 2 unpaired electron, put it in the formula, we will get root 8 bm. You can solve root 8. Then what about spin? No unpaired electron, low spin. It has 2 unpaired electron. So due to the presence of 2 unpaired electron, the spin of the complex will be little high compared to these 2 complexes. Okay. What kind of questions you may expect based on this? Several questions you can compare. NiCO4, NiCN4. Both of them have coordination number 4, both of them have same metal, but NiCO4 it has the geometry of tetrahedral, but NiCN4 the geometry is square planar. That makes one question. And another question, this follows sp3 hybridization, this follows dsp2 hybridization. Why? That makes another question. So where you are finding the difference when you are summarizing, that makes the question for the complexes. Similarly, you can compare. Here you may find it is a zero oxidation state, but in these cases nickel it is in its +2 state only, but both of them are differing in their geometry as well as in their hybridization. Moreover, that cyanido group that becomes the diamagnetic, but the chloride complexes that makes paramagnetic. So you can have three types of question. Why do they have differ in their hybridization, or it is square planar but chloride complex is tetrahedral, or the cyanide complex is diamagnetic while chloride complex is paramagnetic? For all these questions you have to represent the same answer. Okay, now let us find some of the complexes having coordination number 6. Let us find some examples of the complexes having coordination number 6. Here we have taken the complexes of iron and cobalt. Iron atomic number 26, cobalt atomic number 27. So its electronic configuration of iron, argon 3d6 4s2 4p0 and cobalt argon 3d7 4s2. In these cases we have to identify the oxidation state of central metal ion. So we know the cyanide is negative ligand, there are 6. So minus 6 equal to 4 minus, that becomes equal to 2. So oxidation state of iron in this complex is +2. Here minus 6, that side +6, +6, 3 minus +3. So here the oxidation state of iron is +3. Here fluoride -1, so 6 into -1 -6, the charge is -3, that side +6, 3 minus, so cobalt also in its +3 oxidation state. So depends upon the oxidation state of the central metal ion that many electrons to be lost by the metal from their outer shell. So let us find, as it has the Fe2 plus ion, the 2 electron present in 4s orbital is being lost and hence it becomes 4s0, 4p0, 4d0 and 3d orbital it has 6 electron. And let us find what is the strength of the ligand. Cyanide is a strong ligand, so it can pair the d orbital electron. So what happened? The d orbital, it has 4 unpaired electron that makes the 2 set of paired electron. So this pairs like that and this pairs like that. What happened? The 3d orbital being accommodating the 6 electron only in its 3 orientation. So rest of the 2d orbital we will avail as vacant orbital. And what is the coordination number? 6. So we have the 2 vacant orbital of d and 1 s orbital as well as the 3 p orbital that makes the vacant orbital of 6 and hence the metal ion Fe2 plus that undergoes D2sp3 hybridization. So you may find the 3d orbital is n-1 d orbital and these are ns orbital. So as the d orbital utilized for the hybridization is inner d orbital and hence the complex we are saying inner orbital complex. And the hybridized orbital, in the hybridization you may find the d orbital that follows sp orbital. Clear? So D2sp3 is the hybridization. So to these 6 vacant hybrid orbitals of metal ion, the 6 cyanide ligands that provides its electron pair to make a bond with metal ion. So let us summarize the hybridization D2sp3. Geometry of this hybridization is octahedral, and magnetic property, the d orbital, it has no unpaired electron and hence it is diamagnetic. For this the magnetic moment is equal to 0. Then what type of the complex is? It has made use of the inner d orbital. So it is the inner orbital complex, and moreover the d orbital has no unpaired electron, so it is said to be low spin complex. Let us find Fe3. So in this case iron, it is in +3 oxidation state, so it has to lose 3 electron. So 2 of the electron from the 4s orbital and 1 of the electron from the d orbital, that makes to lose 3 plus. So we are getting 3d5 4s 0. So in Fe3 plus, the d orbital contains 5 electron and sp orbitals are vacant. Once again, compare the strength of the ligand. Cyanide, strong ligand, so it can pair the unpaired electrons of a 3d orbital. So what we can have, this electron being paired and this electron becomes over here, it makes a 3d5. So once again, out of 5 orientation of d orbital, I have so 3d5. So what happened? All these 5 electrons to be paired up by the cyanide ligand. So when it is making that, you may find this pairs up and these 2 pairs up and 1 unpaired electron we have. So only 3 orbital that accommodate the 5 electrons in its 3d orbital. So out of 5 orientation, we got 3 in its orbital level, and 2 of the d orbital gets hybridized with the 4s and 4p orbital. Therefore, the hybridization of Fe3 plus ion in this complex is D2sp3. So here you may find 6 vacant orbital. To those vacant orbital, the 6 cyanide ligand can provide the electron. Therefore, we have the complex of the type FeCN6 3-, whose hybridization once again D2sp3. FeCN6 4- also D2sp3. So both of them have same hybridization and same geometry also. But when you find out that magnetic property, this ferric, that Fe3 plus ion, that make the complex paramagnetic, but here the complex is diamagnetic, and hence due to the presence of 1 unpaired electron in its 3d5 orbital, what happened, its magnetic moment, it becomes 1.732 Bohr magneton, and complex once again the inner d orbital, n-1 d orbital is alone utilized, and hence it is inner orbital complex. It is almost low spin because as it has only 1 electron. Because I am going to compare this complex with that other one. You may find what is the large difference between the spinning of the complex. Okay. What is the possible question of these 2 complexes? Because both of them have same hybridization, same geometry, but they do differ in their magnetic property. So the question may arise like that. FeCN4 4- is a diamagnetic complex, while FeCN6 3- is a paramagnetic complex. Why? You have to explain the same thing. Due to the presence of 1 unpaired electron in 3d5 orbital, that makes these complexes paramagnetic. That's all the solution you can give. Let us find the next one. CO F6 3-. In this case also the cobalt is present in its +3 oxidation state. So 2 of the electron from the 4s orbital and 1 of the electron from the 3d orbital is being lost, and hence we have CO3 plus. So 2 plus 1 3, so 7 reduced to 3d6. We have 3d6 4s 4p orbital. I have given here 4d also. So we can write 4p 0, 4d 0. Why? See that in this case the fluoride is weak ligand. So it will not pair the inner d orbital electron. Inner d orbital it has 4 unpaired electron. Due to the weak field nature of fluoride ligand, it unable to pair the n-1d orbital of CO3 plus ion. But anyhow, it needs 6 vacant orbital because of its coordination number is 6. So what it will do? It can make use of 4s orbital, 4p orbital and 4d orbital. So now you are taking the orbital from the outer orbital. So the complex formed by this way is said to be outer orbital complex. So we can have the sp3d2 hybridized orbital. You may find the difference of representation of hybridization of these 3 complexes. When you find D2sp3, DsP2, that a D becomes the first one, that makes the d orbital is from its inner orbital. Or if you find the d orbital after sp orbital like this, that you can find where it is outer orbital. That makes the difference of inner and outer. From the hybridization itself we can identify whether the complex belongs to inner orbital or the outer orbital. So this makes the part of outer orbital because the 4d orbital, so 1 s orbital, 3p orbital and the 2d orbital that hybridized to form sp3d2 hybridized orbital. So to these 6 vacant hybridized orbital of cobalt 3 plus ion, the 6 fluoride ion provides its electron pair to make a bond. Now summarize hybridization sp3d2. Whether the hybridization D2sp3 or even sp3d2, that makes octahedral only. So the geometry of the complex is octahedral. Magnetic behavior, you may find it has 4 unpaired electron in its 3d orbital and hence it becomes paramagnetic. So the magnetic moment 4 into 4 plus 2, 6 4s are 24 we have. So 24 Bohr magneton. Now what type of the complex is? It is outer orbital complex and it is a high spin complex. Why it is high spin? It has 4 unpaired electron in its 3d orbital. So compared to FeCN6 3 minus with the COF6 3 minus, this is low spin but cobalt complex is high spin complex. That's all. The application of BB theory for the formation of complexes having the coordination number 4 and coordination number 6. The next one, limitations of valence bond theory. Valence bond theory mainly explains about the formation of complexes based on lot of assumptions only. So it does not predict a clear and exact reason for the formation of complexes based on different aspects. Let us find one by one. It does provides only qualitative explanations. Qualitative means ligand, weak field, strong field. Complex, para, dia. Inner complex, outer complex. So these are just assumed by the BB theory, but there is no any quantitative interpretations for such type of complexes. Quantitative interpretations means it has some quantitatively some data has to be provided to explain about the formation of the complexes based on their strength of the ligand or the hybridization of the central metal ion. Such explanations does not provide by the VB theory. And it does not provide quantitative interpretation of magnetic properties. We are assuming due to the hybridization, because of the strength of the ligands, strong field it pushes the electron, weak field it does not pair the electron. We are assuming based on that only we are saying the magnetic properties of the complexes. So the magnetic property of the complexes unable to explain by VB theory quantitatively. And it does not provide a qualitative interpretation of stability of the complexes in terms of kinetic and thermodynamic factors. Kinetic factors that determines how fast the complexes are formed. The rate of formation of complexes has to be discussed under kinetic factor. Thermodynamic factor always discuss about the stability of the complexes in terms of Gibbs free energy. And Gibbs free energy, if at all negative, we can say the complexes will be formed and becomes more stable. But such interpretations unable to provide by VB theory. The next one, for coordination number 4, we are saying depends on the hybridization, the complex can have tetrahedral or square planar, but it does not give exact explanation for the formation of complexes, why it is tetrahedral or why it is square planar besides that hybridized orbital. Then it does not provide the reason for outer and inner orbitals used for the hybridization, because it speaks about the strength of the field. So to determine the strength of the field also, it has no any quantitative relationship to compare the strength of the field, that is the ligand field. So it does not predict the stability of the complexes also, and it does not take into account of d orbital splitting. D orbital it has 5 orientation that can split up into T2G orbital and EG orbital. Such splitting of d orbital is not at all discussed in VB theory and does not explain about the strength of the ligand. We are assuming if at all cyanide or carbon monoxide or ethane 1,2 diamine, those are said to be strong, but there is no reason for why these ligands are strong, or the fluoride, chloride, halide, water, why those are weak. For those, the strength of the ligands, it doesn't provide any exact information, or even there is no any interpretations. The next one, it does not explain about the color of the complexes. Werner theory also that explains it speaks about the color of the complexes, but it does not provide any informations or any interpretations why the complexes are colored. Same way, VB theory also unable to explain about the color of the complexes. That's all the valence bond theory, by which we just discussed about the important postulates of VB theory, followed by its applications in the formation of complexes having coordination number 4 and coordination number 6. Also, we discussed about the shortcomings of VB theory. Okay students, let us close our today's session and we will continue the same chapter in our following sessions also. Until then, bye bye.